Hello everyone, my name is Jung-woo Kim. Today I'm going to present our research on indoor positioning using LSTM with turning point alignment, which we call LSTM TPA for short. This presentation is organized into 4 parts. First, I will discuss the background. Second, I will introduce our proposed method LSTM with turning point alignment. Third, I will describe the simulation setup and present the results. Finally, I will conclude by summarizing the key findings and discussing their implications for real-world applications. Indoor positioning is required in many fields like malls, airports, hospitals, and disaster situations. As you can see, location-based services are already a part of our daily lives. Currently, the most common positioning method is GPS. Outdoors, GPS offers very high accuracy. However, indoors, GPS signals are weak or blocked, making it unreliable. As alternatives, infrastructure-based methods such as Wi-Fi, BLE, and UWB have been studied. However, they require high deployment costs and sensitive to environmental changes and may not function reliably in emergencies. On the other hand, infrastructure-independent methods do not require additional infrastructure and primarily rely on sensors, making them cost-effective and scalable. A representative infrastructure-independent method is PDR. PDR estimates position by integrating IMU sensor data. It works without GPS or additional infrastructure and is relatively easy to implement. However, it has just major limitations. Because of sensor noise and bias, cumulative drift errors inevitably occur. On the right, you can see the ground truth trajectory in dashed black and the PDR trajectory in blue. At first glance, the overall shape looks similar, but if you look closely, 2 major problems appear. First, notice that the blue path shakes irregularly at almost every step. These step-level errors accumulate because each step is calculated by integrating IMU signals. Even smooth sensor noise at every step adds up, and the total distance becomes increasingly inaccurate. As a result, the trajectory not only looks noisy, but the walking distance is miscalculated. Second, headings estimation at turning points is inaccurate. Because of this, straight segments gradually drift and fail to stay parallel to the actual path. So also, PDR is simple and infrastructure-free. It clearly suffers from step errors and heading drift. To overcome these issues, we applied LSTM, a recurrent neural network specialized for time series data. LSTM can run stride lengths from IMU signals and capture non-linear walking patterns, which leads to more stable estimates. LSTM is powerful for time series running because it uses gates. These gates include the forget gate, input gate, and output gate. They decide what past information to discard, what new information to store, and what to pass on. Sequential IMU signals are processed through gate cells, allowing the model to run working dynamics. On the right, you can see the trajectory estimated by LSTM compared with the ground truth. Compared to PDR, the irregular shaking at each step is greatly reduced, and the turns are represented more consistently. Still, Cumulative drift remains, so we apply an additional correction method calling turning point alignment, or TPA. In indoor environments, the available space and turning angles are usually fixed, for example 90-degree turns in corridors. This makes turning points reliable anchors that we can use as references. Based on this idea, TPA leverages turning points as anchors. On the left, you can see that snapping removes small fluctuations and highlights only the clear turning points. On the right, the ground truth space is divided into straight segments at these anchors. By aligning each segment to its corresponding turning point, accumulated distance errors are corrected, resulting in a trajectory that better matches the ground truth. Here is the overall framework of our proposed method. First, IMU data is like accelerator, gyroscope, magnetometer, and quaternions are collected. We used quaternions instead of Euler angles to avoid gimbal lock and ensure stable orientation. The LSTM network runs stride ranks, improving robustness against noise. Then, TPA corrects cumulative drift by aligning turning points. The result is a trajectory that is both accurate and stable without external infrastructure. For evaluation, we set up test beds on the 7th floor and basement floor of Chanbi-tor at Gwangwon University. Markers are placed every 3 meters along straight paths. We attached an IMU sensor to the subject's right foot and collected data via Arduino Mega and a laptop. We used mean perpendicular distance, it calls MPD, as the evaluation metric. It evaluates the similarity of the entire trajectory, making it more comprehensive. On the 7th floor, with IMU only, MPD was 1.69 meters. With LSTM, it improved to 0.429 meters, which is about a 75% reduction. And with LSTM TPA, the error further decreased to 0.107 meters, a 93.7% improvement over IMU and 75.1% over LSTM. In the basement, the environment was more challenging due to a larger scale and frequent turns. With IMU only, MPD was 1.77 meters. With LSTM, it dropped to 1.731 meters. However, with LSTM TPA, the error was reduced drastically to 0.106 meters, a 94% improvement over IMU and 91.9% over LSTM. Compared with the 7th floor results, we can see that the benefit of LSTM was much smaller in the basement. This shows that in more complex environments with frequent turns, LSTM's effectiveness is reduced. But even in such conditions, LSTM TPA was able to maintain very high accuracy. In summary, our method achieved over 90% error reduction in both 7th floor and basement experiments. This shows consistent performance across both simple and complex indoor environments. It does not require any additional infrastructure. To conclude, our proposed LSTM with turning point alignment significantly improves indoor positioning accuracy. It effectively reduces cumulative drift compared to both IMU only and conventional LSTM methods. Across different environments, it achieved over 90% accuracy improvement. Another important point is that our method is infrastructure independent. Indoor turning points are usually predictable since location and angles are often limited, such as corridor corners. By leveraging this constraint, the method remains robust across varied floor plans. That concludes my presentation. Here are the references that supported this research. Thank you for your attention.